All right, let's dive into something that's like the secret language your computer uses every single second: data types. It might sound a bit technical, but trust me, it's the key to understanding how everything on your screen actually works.
So think about it for a second. How does your computer know that when you type 25, it's a number, something you can do math with, but when you type Alex, that's a name? I mean, to a machine, it's all just data, right? Well, the answer to that question is pretty much the foundation for all software. See, to handle all this different information, computers need a system, a way to put everything in its proper place. It's kind of like organizing your kitchen, you know? You wouldn't store milk in a salt shaker, and computers, they need the exact right containers for the exact right kind of information. And that system, it's all built around this idea of a data type. You can think of it like a label on a container. This label tells the computer two super critical things. First, how much space to set aside for the data, and second, what you're actually allowed to do with it. This is what stops total chaos, like trying to multiply your name by your age. That would just break everything, right?
Okay, so let's pop open the programmer's digital toolbox. Inside, we're going to find the most basic, most essential tools. These are called primitive data types, and they are the absolute building blocks that pretty much everything else is made of. Now, everything really starts with these primitives. Think of them like individual bricks. They're simple, they're strong, they're fundamental. And just like with real bricks, you can use them to build much more complex things, like a whole house. But before you can build a house, you've got to understand the bricks, right? All right, first up in our toolbox, numbers. Now, you and I might think a number is just a number, but for a computer, it's not quite that simple. To be really efficient, it needs different kinds of containers for different kinds of numbers. So the most common types you'll see are for integers. These are just your everyday whole numbers, no fractions, no decimals. We use them for counting stuff, like 10 students in a class, 365 days in a year, or maybe -5 degrees outside. Let's take a look at a few of the most common sizes. We'll start with the smallest one, the byte. Now, because it uses so little memory, it's super efficient. So if you know for a fact that your number is going to be pretty small, say between -128 and 127, like a person's age, using a byte is a smart move. It saves space and can actually make your program a little bit faster. Next up is the real workhorse of the integer world, the int. Its range is just massive. We're talking over 2 billion in either direction. This makes it the perfect, go-to, reliable choice for most of the whole numbers you'll ever need to work with. And then, for those times when you need to count, say, all the stars in the galaxy, or track milliseconds since the beginning of the computer age, you've got the long. It holds an absolutely astronomical number. This is the heavy-duty container you bring out when an int just won't cut it. But wait a minute, what about prices, like 1999? Or scientific numbers, like pi? Integers can't handle those. For any numbers that have a decimal point, we need a totally different set of tools, the floating point types. And here, we basically have two main options. There's the float, which is great when you need speed, and you're okay with a little less precision, think simple things like currency. But for most modern computers, double is the new standard. It offers, well, double the precision, which makes it way more accurate for tricky scientific or complex calculations. All right, so we've got numbers covered pretty well. But programs are about way more than just math, right? They're also about handling text and, crucially, making decisions. So let's look at the containers for logic and letters. So meet the char. It's a tiny little container that holds just a single character. This could be the letter A, a $sign, or even the number 5, as long as it's treated as text. It's all based on a standard called Unicode, which is basically this giant universal library of every character from every language you can think of. This is what makes sure your code can handle anything from English to an emoji. And here we have what might be the most important data type of all, the Boolean. It is incredibly simple. It can only hold one of two values, true or false. That's it. But think about it. This is the foundation of all decision-making in a program. Is the user logged in? True or false? Is the password correct? True or false? It's all handled by this simple little on-off switch. Okay, so now we have all these cool, specialized containers. But, having a box for integers and another box for characters isn't all that useful if we don't put labels on them. I mean, how would we ever find our data again? And that is exactly where variables come in. A variable is just the name you give to your data. It's the label you stick on that container we've been talking about. That label points to a specific spot in the computer's memory, which lets you easily store your value and then come back and find it again later.
And here's a perfect example of how it all clicks together. We see int days equals 279. So int is our data type, that's the container. Days is the variable name, that's our label. And 279, that's the actual value we're storing inside. See? Simple as that.
Now, you can't just name a variable whatever you want. There are a few rules. It has to start with a letter, a $, or an underscore, and you can't use a word that's already reserved by the programming language. But honestly, the most important rule for writing good code is to make the name meaningful. Student age is 1,000 times better and more helpful than just calling it X. And just to be clear, here are a few classic mistakes people make. You can't start a variable name with a number. You can't use weird symbols like a hashtag at the beginning, and you absolutely cannot have spaces in your variable names. Any of these will just give you an error.
Finally, you might hear programmers throw around the term literal. It sounds all technical and fancy, but it's actually super simple. The literal is just the fixed value itself. So in these examples, the number 100, that's an integer literal. The single letter J, that's a character literal. The word true is a Boolean literal, and the phrase hello is a string literal. It's literally just the data itself. Okay, so let's zoom back out for a second. We've looked at the containers, we've talked about the labels, and we've seen the values themselves. What we've really done is assemble the most fundamental, rock-solid pieces of any computer program. And really, that's the big takeaway here. Every single piece of software you use, from the most mind-blowing video game to the simplest calculator app on your phone, is built by combining these very simple data types in new and creative ways. They are the true building blocks, the atoms of our digital world. So you see, understanding these data types isn't just some boring theory. It's the first real step to creation. It gives you the language you need to talk to a machine and bring your ideas to life. These are the building blocks. The only question left is, what are you going to imagine with them?